This is part 3 of a series of videos on how to do analytics for bivariate data. In part 3, we will look at the case where both the variables are qualitative in nature. So we have these two examples. I have 25 orders and my qualitative variables are category and state. And this is a second example, same fields, slightly different data, slightly different frequencies. So right now there are no numbers involved here, so we really cannot do anything. We cannot do any analytics with this. We cannot plot any charts, we cannot compute any numerical measures to say anything. So the first thing we have to do is create a frequency table, a two-dimensional frequency table, which is called a contingency table. So we will first learn how to create a contingency table. There are two approaches. One is using the count if s function and the other is using pivot tables. So let's first use the first approach, using the count if s approach. To save some time, I have already created a template for the contingency table and I'll bring it here just now. Here, this is my template. So we will write some formulas here to get the frequencies of Florida appliances, Florida furniture, Florida technology, and so on. So the first thing we will do is we will name these ranges. So I have two ranges for category. I'm going to name this one category 1. And I will name this one category 2. Define name category 2. And I will name this one state 1. And I'll define this one state 2. Define name state 2. Okay. So now this contingency table we will make using the equal to count if s function. So we had learned how to use the count if function to generate frequencies for univariate data. Now we have bivariate data. So we use count if s, where s stands for a series. So we have a series of two columns. So we will write count if s. So the first criteria is state. So state 1, and the criteria is Florida, which is sitting in cell I6, comma, category 1, comma, appliances. So 4 is the frequency for Florida appliances. Now before I copy it to the rest of this table, we'll put some dollar signs. So we'll put a dollar sign in front of the I, because when we copy this formula to the right, I will want to become j, but we don't want that. We want I to stay I because column I has the state names. And this j will want to become k, which is okay, that's what we want. But when we copy this formula down, this 5 will want to become 6, but we want to keep it at 5, so we'll put a dollar sign in front of the 5. Okay, now we can copy this formula to the right and all this here, and that's it. We have a contingency table of frequencies. It's a two-dimensional frequency table using the count if s function. The other approach is creating the contingency table using the pivot table approach. So we'll show you how to do that now using pivot tables. So we will select the database. So the frequency is for order numbers, where we want to put state in rows and category in column. So we will say insert pivot table, existing sheet, and location. Let's suppose we want this table to appear here. Okay. Okay. So what do we want? We want state in rows, we want category in column, and we want count of order ID. So we'll put order ID in values and it will have count of order ID. And that's it, our frequency table is created. So this is a much faster way to create frequency tables. We don't have to know how the COUNTIF-S function works, but it's always good to know how the COUNTIF-S function works. You might use it for something else. But here, there is a faster way to get the contingency table using pivot tables. Okay, the next thing we learn is how to create the expected frequency table, assuming state and category columns are independent of each other. So once we have created the contingency table, which we have, we are ready to create the expected frequency table. So the way the expected frequency table works is, we want to write a formula to generate the expected frequency for Florida appliances. So we look at the row sum for Florida multiplied by the column sum of appliances and divided by the total sum. So row sum multiplied by column sum divided by total sum. That's the formula. So 4.68 is the expected frequency. Now before we copy and paste this, let's put some dollar signs. So we want to copy this formula to the right. So when we copy to the right, M will want to become N, but we can't allow that. So we put a dollar sign in front of the M, and the J will want to become K, which is fine, which is what we want. When we copy this formula down, this 6 will want to become 7, which is fine, that's what we want. And this 10 will want to become 11, which we don't want, so we put a dollar sign in front of the 10. And this M10, we have to put a dollar sign in front of both M and 10 because M10 is the total frequency which is fixed. Okay, now we are ready to copy this formula here and copy it here. So what we have to make sure is that the total frequencies match in these two tables, but the individual frequencies will vary. Okay, we'll get back to expected frequency table after we have drawn some charts. So once we have the frequencies, what kind of charts can we draw? We can draw clustered columns, stacked columns, clustered bar chart, and stacked bar charts. So insert, that's a clustered column chart. So we have clusters of columns for each state, and since there are 3 categories, the cluster has 3 columns. So basically this is a frequency distribution of all the orders distributed over state and category combination. We can create another chart, insert a stacked column chart. So that's a stacked column chart. And I'm not writing the titles to save some time, but when I save this file for posting, I will have added some titles. So this is a stacked column chart. So the frequencies are stacked up in one column. So the advantage here is you can see the total frequency for each state, and within each column you can generally see how the frequencies are distributed. Similarly, you can create a clustered bar chart, which is just a clustered column chart rotated by 90 degrees. And we can also create a stacked bar chart. So those are some charts you can create using this contingency table. We don't do any charts using the expected frequency table. That is used for another purpose. And now actually we are ready to use the expected frequency table. So what do we use expected frequency table for? For a chi-square test. So chi-square test is a test for checking if there is a relationship or an association between the two qualitative variables. And the way it is done is, there's a function called chi-square.test, and you specify the actual frequency range and the expected frequency range. So what the chi-square test does is it figures out how close the actual frequencies are to the expected frequencies. And if they're very close, this chi-square test generates a high value. But if there's a big difference between the actual frequencies and the expected frequencies, this chi-square test generates a small value. Okay, so the smaller the value generated here, the larger the difference between these two sets of frequencies. So let's see how we do. We get 0.559 or 0.56 approximately. So that's a very high number. So this number varies from 0 to 1, but anything over 0.05 is considered big. Of course, bigger the number, closer it gets to 1, less the difference between actual and expected. Now you can see 4, 4.68, very close. 5, 5.2, very close. 4, 3.12, quite close. And that's the reason why this value, which is actually called the p-value, let me label it, p-value using the chi-square test. Okay, so since this value is greater than 0.05, we can conclude that there is no association between the two variables. So that's the chi-square test. Now we have another example. In this example, we have modified the data just a little bit so that for this example, the chi-square test will show us that there is a relationship between them. So what we will do is we'll copy these two and we'll move these charts just a little bit. Now here we will rewrite these functions. Okay, so equal to count if S, this time it's going to be state 2 comma this Florida, and category 2 comma appliances. And now we'll put the necessary dollar signs. So we'll put a dollar sign in front of the I and a dollar sign in front of the 33. And now we can copy and paste this formula. So those are the new frequencies, and using these frequencies we've computed the expected frequencies, but since the total frequencies are the same here and here, and these are the same here and here, the expected frequencies are identical from here and here. So anyway, we can do a new chi-square test. P-value equal to chi-square dot test. Actual range of frequencies is this, and the expected range of frequencies is this. So this time, because there's a high gap between actual and expected, the p-value is going to be low. So let's see how low we get. 0.02. So that's low because it's lower than 0.05. So here we can say that since this value is less than 0.05, we can conclude that there is an association between the two variables. Now if we generate a stacked column chart using the new frequencies, you can see that something is going on. If it's Florida customers are ordering more furniture. Georgia customers are not ordering any furniture. Georgia customers are ordering more appliances. Florida customers are not ordering that many appliances. So there's some association between state and the category, which is what is reflected in this p-value, and which is what is reflected in the difference between the expected and actual frequencies. So this concludes this lesson on analytics for bivariate data where both the variables are qualitative in nature.